We're back, and now we're going to talk about another kind of wave. The slinkies were all about compression waves, with waves that go back and forth the same way as the wave is propagating. The book calls those longitudinal waves. Now we're going to be looking at transverse waves in which the medium is moving perpendicular to the direction the wave is traveling. This is like the wave in a football stadium. The people are moving up and down, and the wave goes sideways. These two things do not have to be the same, and it's perfectly okay for them to be different. Sometimes you get both types. If you look at what the earthquake people do, they deal with two very different kinds of waves that travel at very different speeds. And as a matter of fact, by timing the interval between when the two waves arrive at their sensor, they can tell how far away it was. So let's talk about transverse waves. What's this about? Well, the basic idea is a wave in a string. We have a rope here, it moves up and down, and the wave goes that way. How does the physics of all this work out? Well, in your book, you'll find a derivation for the velocity of a transverse wave. And the velocity of a transverse wave depends upon the tension in the string. It also depends on the mass density in the string. Mass density is just the mass of the whole string divided by its length. So you wind up with something in kilograms per meter for mass density. Now, by changing these things, you can change the velocity of a wave. The formula turns out to be that v equals the square root of t over mu. Now, where can you see this happening? Well, probably the best place to look at it is in a guitar. In a guitar, we have 6 strings in a standard guitar. The strings make different notes. The way they make different notes is they have different velocities for waves in the string. Now, there are a lot of weird things, there's a lot of constraints about a guitar. First off, all the strings have to be the same length. They cannot have an extra long string and a short string. Guitars just aren't made that way. Pianos can do that, but not guitars. The other thing is that the way a guitar is built, you really want all the strings to be roughly at the same tension. Not precisely, but something close. And that's because if one of the strings was at a much bigger tension than the other ones, you'd have a lopsided pull on the neck, and your guitar would eventually warp and stop being playable. So you have to have the same length and the same tension, more or less. I mean, you adjust the tension with little turning knobs, but those two things have to be sort of the same. To get different notes, the only thing left to change is the mass density. And if you look at a guitar, you will see that the different strings are made very differently. The higher strings are really thin wire, and as you go down through the guitar, the very lowest strings are really, really thick wire. And that's just because that way you can have all 6 strings be the same length, have roughly the same tension, and get different velocities and hence different notes out of them. In a piano, they do the same sort of thing. The thick strings are for low notes. They're much thicker than the high strings, but they can also change the length. The high strings are a lot shorter in a piano. And all the stringed instruments, violas and so on, have the same kind of constraints. So how does the velocity change the frequency? Every note has a certain frequency. That's just how often the medium is bouncing back and forth in a second. Well, it turns out that that formula is given by this. The frequency of the lowest oscillation is the velocity divided by 2 times the length of the string. So the frequency is it's 1 over the time it would take for a wave to propagate twice the length of the string. When we look at standing waves in our next bit, we'll kind of start to see why that works out. So that's what there is to know about transverse waves. They involve the medium particles moving perpendicular to the direction in that the wave moves. They depend on the tension and the mass density. The velocity of the wave is given by this formula. And if you have a standing wave in a string, its lowest frequency is given by that. Okay, now we're going to do some experiments with waves in a string. But first we've got to talk about yet another distinction waves have, and this is the difference between traveling waves and standing waves. And what's that distinction? Well, the basic idea is that if you have waves in a string that's tied to a wall at both ends, okay, so it's tied to something very large. You can make waves in the middle of the string. They're just disturbances, and that travel down the string, and they travel this way, blah, 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 until they hit the wall, and then they bounce back. And it turns out that if the string is tied rigidly to a wall, when they bounce back, they are going up if they were going up when they hit the wall. So you get this wave pulse now traveling back this way. And you could do that. You would have a little wave pulse that goes zzz, down the string, hits the wall, bounces back. That's a traveling wave. The wave is actually moving and going somewhere. That's one kind of wave. There's another kind of wave. And this wave is what you get if you have a string. And instead of having a little pulse that goes from one end to the other, we move the whole wave like that. And what happens with this? Well, if you have a wave like this, there are 2 ways to think about it. One is that this disturbance goes down, reflects off the wall, and comes back, and this one goes this way and bounces off that and comes back. The other way to think about it is just that this bounces back and forth like that, and this one bounces back and forth like that. And so you get the whole string doing something like this. Boing, 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 boing. This is known as a standing wave. This is a wave that doesn't go anyplace. It only happens when you have hard walls on either edge. And it just bounces back and forth. This is the kind of wave that the guitar string has. This is the wave most musical instruments are aiming at. You just bounce things back and forth. This isn't the only standing wave. There are others. This is just the easiest one to draw. You can draw another one that looks just, instead of having 2 lumps, it just has 1. And this goes back and forth like so. This is actually what a guitar string mostly does. Most of a guitar string oscillating is like this. There's a little bit of that one. And there are many more. You can have standing waves that have 3 lumps, 4, 5, 6, whatever. These are different harmonics, they're different frequencies. It turns out that the note these things make, if you call this note of a guitar string the fundamental, then this will be 2 times the fundamental. That will be 3 times, and so on. And these notes you can calculate from the velocity. Remember, the velocity of a traveling wave in a string is given by T over mu. Well, the frequency of the lowest note is V over 2L. And the next one up is V over L. And so on.